Okay, large deviations principle. So large deviations principle started from the time of Cramer. You might have all heard of Herald. Who was an actuary working for an insurance company. And so he had to do something for the insurance company. So he modeled the problem as follows. Let's say that P is the premium that you receive per day. So you can average it. You have some 100 customers, they pay premium and then average it so that it's per day. Received per day by the company. And there are also claims. So people lose houses or whatever, right? Or boats and so on. And then they're going to put a claim. And the claims are going to be first day, let's say, there is X1 in some currency. Okay? This is the size of the claims. And then the second day, somebody else comes and says the car is stolen, whatever. Right? So sizes of claims. So these are all, let's say, IID random variables. What does that mean? Identically distributed. That means they all look alike but independent. That's a natural assumption to make, right? Then he wanted to find the probability that the summation of xi, I varying from 1 to n, let's say. All right, so this is the total number of claims in the first n days. If it is greater than n times p, that's bad for the company, right? So because the amount of premium they receive exceeds the claims, right? So he wanted to see, he had to study this. And what can one do? Yeah. Oh, it's in Sweden, right? He's a Swedish mathematician. But at that time, I think he rose from very humble beginnings. He was just an actuary working for an insurance company. And I don't know the name of the company. Yeah. One can Google search nowadays, right? And maybe one of them would tell me right away. So he worked on it. See, if a problem is given to us like this, we may say, well, I don't know, I know probability, what is omega f p, something like that, right? And we'll get confused and then bide for time. But what he did was, he took some lambda greater than 0, any lambda greater than 0, and summation xi, he said, is np lambda. P is not a probability here, premium per day. Bad choice of notation, right? And then what he did was, he said, well, he would raise both sides to the power e, meaning exponentiate both sides. And then he said, well, this is therefore np lambda times expected value of e to the lambda summation xi. Right? Huh? Is that okay? Yeah. You all know this inequality, right? Okay. This is just Markov inequality or whatever name. You don't even have to give it a name. It's so easy. And then what did he do? Let's see. Independence, so it can factor out, right? We'll call it as m of lambda. Since the same m of lambda is coming in, I'll call it as to the power n, because I varies from 1 to n, you all know that if there is independence, the so-called Laplace transform or moment generating functions becomes the product. What is m of lambda? E to the lambda x1, let's say. Since they are all IID, whether you put x1 or x2 or whatever, it's the same. Okay? So where? Therefore, take a logarithm. Now you can even write it as 1 over n times summation xi by dividing just within here. Then that would become less than or equal to n times logarithm of m of lambda minus np lambda, right? So he was able to write something. That's nice for an actuary. And then you can, there is an n everywhere, so he brought it here. Oh, logarithm. This is called x bar because it's the average arithmetic mean greater than p, less than or equal to, you can even pull out a minus, and there is no n now, right? Because it has come here. P lambda minus logarithm of m of lambda. Okay, therefore, this quantity will be less than or equal to no matter what lambda you take, right? So you can inf over lambda. But then there is a minus sign, so it becomes minus sup. So this quantity will be also less than or equal to supremum over lambda positive of so m of lambda in probability theory is called moment generating function, and we assume that the MGF exists, moment generating function exists, especially near the origin, and so that it can generate moments and so on. So think of xi's as nice enough random variables, right? And then he showed that this actually is over all lambda. Well, that's not very difficult to believe, right? Over all lambda. Well, you want us to show it. Okay. All right. And then you can even take the limit as n goes to infinity. On this side, let's take the limit, lim sup rather, because limit need not exist, right? So long range average, I think I'm leaving some things, 1 over n, x bar greater than p. So this was his inequality. This is called the upper bound. There is also a corresponding lower bound and so on. And it is this function that we will call as I of lambda. Why I of lambda? I of p? No, I of lambda.
This is a conjugate of log n lambda.
Pardon? Yeah, minus I of p. Yeah, it is the Fenchel, yeah, Legendre-Fenchel transform, yeah, of H, where the Hamiltonian is logarithm of m of lambda. So this is the first example of this kind of study, and motivated by this, because there is only one. Okay, correct. Because I'm suping over lambda, I cannot call it as I of lambda, it's nonsensical. So it is really I of p. That's the whole thing, supremum and so on and so forth. So with the minus sign, that's minus I of p, right? So what was Cramer's theorem? One can write a theorem of Cramer saying that there is this inequality becomes an equality if limit exists. In which case, in other words, this upper bound is very sharp. Any questions so far? Okay, so how will somebody use this? Well, you want this probability to be very small, right? You want this to be a rare event. Therefore, go ahead and control this, right? And make it small. It won't become small just like that. You have to, for some p that you like, it will become like 0.001. So choose a p such that this upper bound becomes, right, makes this probability to be 0.001, then that would be the premium that you fix. You all understand?
So that is your choice.
Yeah, that's, yeah. So what is the premium to be fixed so that this happens with probability e to the minus delta or something, delta given to you, right? So they took logarithm and so on, and you can actually calculate, right? Because m of lambda is, let's say, one can calculate what it is. It's the Laplace transform, right, here. And then put it in, minimize, maximize over lambda, and you get your I of p. So choose a p that gives you, that matches with e to the minus delta. That's all there is to it. So you go back and actually you can interfere with the system, right? You are not just calculating probabilities. Okay. So what is the large deviation principle then? So there is this rate function that shows up.
One day times that is good enough.
Pardon?
One day times will be good enough.
Yeah.
So,
That's right. At that time, it was like this. Yeah. Now, so motivated by this, I can state the large deviations principle. Okay. So, pardon? When was it? When? 40s, huh? Yeah, 40s. Yeah, it's the same Cramer for the Cramer-Rao theorem and all those. Yeah, so given a family of probability measures, P sub epsilon, let's say, epsilon greater than 0. Right? So in this problem, what is P sub n was there, right? We were interested in the probability of x bar, where x bar involved the first n IID variables, right? So the distribution of x bar could be called as P sub n, okay? That's the family that we were talking about there. P sub epsilon. We say that P sub epsilon satisfies large deviation principle with the rate function I. If 1, I is lower semi-continuous. You all know what is lower semi-continuous, right? So take a curve like that, that's lower semi-continuous. Namely, you take the lim inf, right? And the actual value is smaller than that. I is lower semi-continuous. That's just an example, okay? I cannot define something with pictures, okay? And has compact. They say that picture is worth 1,000 words, right? Yeah, but no amount of pictures can equal a theorem, proof. Compact sets too. For all f closed, I'm talking about the state space. Limit as epsilon goes to 0. Whether epsilon goes to 0, there n went to infinity, right? So think of 1 over n as epsilon. It's not a big deal. So you can see 1 over n is epsilon, then there is a logarithm, and then p sub epsilon, right, of f. Okay, limit may not exist, right? So put a lim. that would be less than or equal to minus infimum of X member of F. And for all G open, lim inf of P epsilon epsilon logarithm P epsilon epsilon goes to 0 is greater than or equal to minus infimum of I of X member of G. So if all these are satisfied, then we say that both are infimum. Yeah.
Because here you
Where? Oh, this is lim sup.
this is IP, you are taking the.
That's IP itself. That's the whole definition of IP. But then I have to take I of X as X member of, right? Yeah. I had to minimize. So the minus sign is there, and then I had to inf over the set. So if you inf over, pardon?
Minus must come inside.
Where?
Infimum of the minus IX, right?
No. Let's see.
Over X and then super over.
That's right. There is a minus sign. Let's cancel the minus signs everywhere. Then you have the infimum, right? This is the lim sup part. Okay. So don't look at the minus sign because there is a minus sign here as well. This is I of P. You are supposed to minimize over P. And that would happen because this is X bar member of P to infinity, right? And the lowest will be obtained at P. So now this is complicated looking thing, but then if the limit exists, let's say for a set F or G or whatever, some set wherein okay, if the limit exists for a set, then it all comes out to be exactly minus infimum of I of X. All right. Okay. All right. Let me. So I itself is the Legendre differential transform of log m. Okay, we call it as, right, if you are aware of that. But you don't have to know it now. So next one, I'll quickly go to an infinite dimensional example. I won't prove it. I'll state it and then we will use it in more complicated. This is Schilder's theorem. So take the Brownian motion multiplied by square root of epsilon and call its law as P epsilon. So P epsilon is going to be, but whenever I write this script L, it's the law, meaning the probability distribution. But here it's a whole process, but that shouldn't bother us because, it's on the path space, right? So whether a stochastic process is a bunch, is infinitely many, even uncountably many random variables, or just one random variable taking values in the path space, it's up to you which one you want to use, right? So this is a Brownian motion or Wiener process, whichever way you call it. It's a standard Brownian motion. In dimension 1 or D, it doesn't matter. So we are doing it all on the path space. So what are the values of B? There is B dot bt of omega, right? If you look at, if you fix the omega, that's called the sample function, and it'll be a continuous function. If you are looking only for t between 0 and 1, that means it's a continuous function on the closed interval 0, 1. It starts at time 0 at 0, right? You know all these maybe. So what do we know about this function, about P epsilon? We know that P epsilon converges to delta 0 because everything becomes 0. So I just call it in a fancy way delta 0. So this double means the not implies, I'll just put it as weak convergence. And that is integral of, you take any continuous bounded function, P epsilon dx, it would converge to integral, it will just go to f of 0. F continuous bounded where? I told you that it's all in the path space. Path space can be given a name, we can call it as omega, doesn't matter. So omega here stands for space of continuous functions. Let's say real valued continuous functions on the interval 0, 1. What do I mean by on the interval 0, 1? That's the time interval. Okay? So, so that's the meaning of omega. And we would like to know something more about this convergence. So in other words, let's just write down the rate function. Any questions so far? I have actually gone quickly to path space and so on, but then I won't go further. I'll just work on the path space. So what is omega here? Let me just write down. I'm not convinced you all like it. Then take all the Borel sigma field because there is a natural, how would you metrize it? Soup norms, right? Soup, huh? I could. Or I can say that I work on this space, but I know that these measures do not see other functions. So, right? Those are all sets of measures 0, whichever way. And then F is, let's say, the Borel sigma field in omega. Right? And then P epsilons are given to you, right? That's all there is to it. Okay. Then the rate function, this is Schilder's theorem, okay? I of F. It is equal to integral 0, 1 of F dot. 1/2 is also there. F dot of S ds, and there is a square here. If F is absolutely continuous. Okay, there is not much space there. I'll write it here. These are all known. So you got to read to the right of this I'm writing. If F is absolutely continuous, with F dot meaning derivative of F with respect to S. So it's the time derivative, member of L2. Right? So you can just think of actually, you don't have to think about RD and all that. I'm just working on the interval 0, 1, right? Well, these are actually F of S is a path. Yeah, it's a path. It can be d-dimensional, but we are only talking about it as a function of time. Any questions? Okay. What happens? It is going to be infinity otherwise. So that's what he proved. Now let's quickly go to put this, the meaning of it and all will become clear to what is known as the Friedlin-Ventesel.
Just a
Yeah.
say it is the unequal set of thing, then infimum is actually the first element of the Laplace.
Right. Right. That's right. So this has connections to
It's energy.
Yeah, that's right. It's the energy. So now Friedlin-Ventesel large deviation principle. So how would you use this IFF before we go there, right? I just wrote something. It doesn't look anything like what Kramer would have thought of, right? Well, he might have, but then he didn't come up with it. So what is the intuitive meaning of this, right? So the idea is if you don't have an epsilon, namely epsilon to be 0, the particle is just going to be at 0, right? So you make it move, and then it goes to 0, right? And then you want to find out how it goes to 0, right? There are various ways in which it can go to 0. And on the way, it can also, you may be interested in a certain event which is rare. So within that, if that rare event were to occur, how would it move to 0? So you want to see the dynamics of it. And you want to see the easiest path for it to come to 0 by minimizing this I. I'll explain to you more when I do this Friedlin-Ventesel theory. It's easier somehow when we have an equation. Dx epsilon of P, A and G, I wrote, okay. It can also depend on x epsilon d dt plus square root of epsilon g of t, g of dw of t. And x epsilon of 0 is little x given to us. So let's say that this is the dynamics. So you can think of it as though there is some small noise perturbing an equation which otherwise would have been an ODE, ordinary differential equation. Or you can say that you are putting it in so that you are giving some energy to this process x sub epsilon, x super epsilon, right? So what I was telling you, now I can describe to you. So let's say that this A, for instance, has maybe a double well. So it's a function, well, not this A, the x epsilon, yeah. X epsilon is here, let's say. All right? Or the little x is here. And therefore, everything is just over here. You want to bring it here. But that's not going to happen very easily. So you introduce a noise term. Maybe let's say that G is just identity or something. So it is just square root of epsilon dw. Then the process begins to be moving because of the presence of the Wiener process. And it could go in so many different ways. Maybe there are I don't know how to draw three-dimensional pictures and so on. So it could come around and then come here, or it could go the other way and come here, or it could be foolish enough to go all the way and come here, and so on, right? So there are so many paths, but this is a rare event, right? To bring it from here to here with a small noise. The noise is definitely going to bring, because there is a small chance that it would come here. You all understand? So you call this transition from this well to this well as your event. So the event can be called by any name, A. Then A is a rare event, right? Oh, okay. G, E. E is an event. and it's rare because you are looking at certain transitions that do not happen readily. So the idea is what is the PE epsilon?
And he reaches the other point.
That's right, sometime or the other. Yeah, that it would eventually hit it. Yeah. Right, that's right, that's right. That's why these things happen. And P epsilon of E is going to be like very small. Right? So think of it as though it is going to be some e to the beta or something. Right? And this theory tells you that it is going to be e to the minus infimum of I of x, x member of E. Right? So this, yeah, tell me.
E is the event that you go from one well to the
Other well, yeah. You want it to be restless, right? Otherwise, it will just go to sleep here. To make it restless, we put a square root of epsilon dw, and then there is at least a very fighting chance that it will come here. And you know that it is a positive number, not 0, right? Because Wiener process will definitely activate. However small the probability is, there is some chance. Then call it as e to the minus beta, right? Think it has to be like this. And then write it, maybe there is some rate function, and then that's why it's called a rate function, right? And then make it as e to the minus infimum. So these are all tricks, which Germans call as ansatz. Right? Very good guess, huh? I don't know how to SATZ.
Yeah.
Big A. AN. Oh, that's my N. Yeah.
E will not move it from one well to other.
No, that won't move because it's a deterministic ODE, right?
Two critical points it cannot cross.
That's right. So it cannot cross. Yeah.
Critical point.
That's right. That's right. So you want to make it, give it some. That's why you make it restless and move it out. Okay. So this is it.
Simple example can be manual handling.
Right.
Where you think that it's a gradient of the
Okay. Right.
Yes.
That's right. And you can see when this will be large. I mean, where this infimum is attained. Supposing this infimum is attained at some I of x0, let's say, right? These are all paths that I'm talking about. The little x are all in the path space, right? So then you know that this x0 is the path that you should advertise as the optimal path to take the particle from one place to another, right? So that gives you the right kind of information, because out of all the paths, this will be the optimal path or whatever. Okay, I didn't actually want to say any of these, so I had to hurry up. Okay, so
Tell us how the rate function looks like.
yeah, I will tell you in a minute. Yeah, and we can have G and A to be Lifschitz continuous, whatever you want to have, and G is also, let's say, uniformly elliptic, bounded. You just name it so that there is no problem with solvability, right? And where do you think x epsilon will go? It will converge in distribution. Sometimes right weakly, sometimes in distribution, they're all the same. It will go to, what shall I call it as x super 0, let's say, of t. Plus, no, there is nothing. That's it. Because epsilon has gone to 0, right? x0 of 0 is x. Okay, there are too many zeros, I'm sorry. I could have put a star or something instead of this 0. Okay. Now what is the rate function? That was the question. So Ventesel and Friedlin computed the I for us, okay? And what is I of f? It is similar to what we got in the Schilder's theorem integral. Let's say that these are all done in 0 to capital T. So I'm considering these equations in the interval 0 to T. And it would come out to be f dot of s minus capital A of s, f of s. Okay. Comma. I'll tell you what this is, gamma inverse. Times the same thing. Gamma inverse, I should have put f of s. Yes. F of s. If f dot is, if f is twice differentiable, right? And the derivative is in L2 and so on. If f dot is a member of L2 of 0t, and f of 0 is x, and infinity otherwise. I haven't told you what is gamma, right? So gamma is really GG star. Put in the t and x and all that, right? Then gamma of tx or tf, whatever. So like this. That's all there is to it. Now the question is, why should this be true? I'll show you, at least partly. Before we go, this looks very clumsy. So what Wendell Fleming and others thought was, if f is like this, then let's consider the following equation. If f is as above, define a function v, take any f as above and define a function v. F dot of t is equal to a of t, f of t, dt, f dot of t. Well, it's already the derivative, so I don't have to put a dt plus gv. I can actually see here and write down. G. And let f of 0 be x. So this is a ODE, right? So define call it as a control term, because if you write something by lowercase u or v, it's a good idea to call it as a control. Because solutions of PDEs are also u or v. So what we can do is, then you can see that why would he consider this kind of a thing? Because then f dot minus a, right? Bring it here, and then there is, hit it with g inverse, you just get v. And then the g star part is there, right? So the whole thing can be actually written as I of f equal to 1/2 integral 0 to t v v of s ds, right? Correct? Where v corresponds to what is the meaning of v? It is this v. But there may not be just one v, right? Maybe two different v's give rise to the same f, let's say.
It's the in the relative.
That's true. That's true. That's there. V squared. Correct. That's what I want. And the 1/2 is there. Yeah. Oh, I took the. I'm not going to look at v by itself. Integral of 0 to dot of v. Then its time derivative is just little v. Yeah. 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 Okay. So, if v comma f are connected by equation 1, so let's call this as equation 1, infinity otherwise. But then there may not be just a unique v, so you got to inf over v, right? So with relaxed conditions, with general conditions, on A and G, I of f becomes 1/2 or infimum. Yeah. Infimum, you get inf over all v such that the f is given by this dynamic, such that f dot is a of t f of t plus g of t f of t b of t. And do you all see the dot there? So it's difficult to see dots. And f of 0. So you got to inf over all of these and then compute. So it's all kind of clumsy. Okay. I hope you are able to read this. That's the so from now on what I'll do is I won't write so much. I'll just call it as this equation. I'll just say v such that f is a member of, or f is g0 of integral where g0 of integral 0 to dot v of s ds is another name for solutions of this equation. Got it? Because it depends on v, and then you solve it, and I take any solution, right? Any v that will give me these this f, g naught is another name. For solutions of for solution of equation 1. Okay. We put all these to rest. We'll come back and then see at least one way how one can prove it. Not a full proof, just some ideas. So okay? Yeah. Very good, very good. See, I told you I didn't forget this. Okay, now, any questions so far? So far, I have only talked about one idea, namely large deviations principle. These are all just manipulating and saying, oh, there exists something that was proved by Ventesel and Friedland, right? The nicety of writing it in this way, okay, is that it corresponds to what we wrote for the Brownian motion. Here also just f dot of s squared, right? and so on and so forth. Of course, for the Brownian motion, there was no A and G was 1. So we just had B, right? That's why there was nothing else to do there. All right, now we come to the next Laplace principle. So somebody stated the other day also, so you take an H which is continuous bounded, and you can actually find out the limit of this quantity. So I'll write first take a continuous bounded function on the real line or on 0, 1. Then the limit of 1 over n as n goes to infinity of integral 0 to 1 of e to the minus x. Should I have a division by n here or multiplication by n? Is equal to minus minimum of so that's the classic Laplace principle. It's a good exercise actually. One can prove it by hand. And then here is the so what's happening here is if you think of a random variable which is uniform over 0, 1, this is what you get. So that spurred interest in finding out what happens if there are some other kind of random variables, right? So Bharadhan's Laplace principle. So it concerns, okay, Bharadhan's Laplace principle, I'll first state it as though it's a theorem. Within that theorem, there is this statement. So suppose there is a family of random variables which solves the large deviation principle with rate I. So let's say x epsilon satisfies. That means the probability measures associated with x epsilon, and I wrote some inequalities for open sets, closed sets, and so on, right? Satisfies large deviation principle with rate I. If this is the case, then what he proved was
epsilon is the probability subset with x epsilon.
Right, with the x epsilons. Yeah. So the law of x epsilon is going to be called as P epsilon. Right? Then he proved that the limit as epsilon goes to 0, epsilon times logarithm integral 0 to 1. I cannot do all those. P epsilon, E epsilon. Expectation is good enough. Everything in the exponent. It's the analog, right? It is equal to minus over all x. So there is a rate function that comes in there, right? And so what is that rate function? That's precisely the large deviation principle. So this kind of a statement is what I call as Laplace principle in general. So this is just a particular case, but here x epsilons can be whatever. And H is, this holds for all H CB. It even holds for CB of infinite dimensional spaces, assuming that they are metric spaces, complete separable, things like that. So converse is true. Converse holds. Namely, this is called Laplace principle with rate I. Converse is what? LP implies LDP.
So X epsilons are coming from Brownian motion? I mean, sorry.
Anywhere.
Stochastic differential. No.
It could, yeah, anything. Right, anywhere. Yeah.
Satisfy the large deviation.
That's right. It could come from discrete problems or continuous problems. It could come from finite alphabets and combinatorial problems where your epsilon is just some parameter. Oh, we don't know. If it is in that context, these are all examples. Yeah, that's right. That's right. The rate function can be whatever. It could be the rate function. If your x epsilons are all IID variables, it would be the rate function from the Cramer's theorem. If it is x epsilon is square root of epsilon times b, then we would call I to be the one from Schilder's theorem, things like that. It's a general statement. LDP and LP are therefore equivalent.
It is called a Laplace principle. It is just LP now as p tends to infinity is equal to maximum or minimum.
That's right. This statement was proved by Laplace, I think. So
basically, LP now goes to maximum as.
That's right. That's right. Yeah. That's right. Yeah, that's right. it is somehow called as goes by his name. Okay, now there are. Gaussian diffusions, yeah. Okay. Now let's put all these aside and then go to something that looks disconnected. So now there are two disconnected parts, right? But then there is a connection here. But what I'm saying is, as far as statements are concerned, large deviation principle statement and Laplace principle. A third one. So it may look disconnected. So because we want to now prove or shed some light on Friedland-Ventesel principle. Okay, so let's say that we are again working on the canonical space. Okay, omega is. So we are considering the paths. That's all that I'm saying. And then the f and whatever, right? You can fill it all up. And it is equipped with, let's say, the Gaussian measure. F is the Borel sigma field. And then mu, let's call it. It's the standard Gaussian measure. Could I just call it as Gaussian measure on omega. Then in this, you all know that W of t omega, if you define it to be, omega is a path, right? So what is little omega? It is a general element of capital omega, right? So you can call it as omega of t. Then that's called the, that would be under mu, this would be a Brownian motion. Because we have gone to the space of values of the Brownian motion, path, to the path space itself. Okay. Now there is the, let's say now I want to do the following. W tilde, I'm going to write it as, I don't have to put W of t. Omega is usually suppressed. W of t minus integral, yeah. Where v is some function. Then W tilde need not be a Brownian motion under this measure, but by a change of measure, it can be made as a Brownian motion. That's called the Cameron-Martin-Girsanov theorem. All right. So then W tilde is a Brownian motion. I'll just write Bm under a measure mu sub v, let's call it, where with respect to mu is given by e to the integral 0 to t v of s d w of s minus integral 0 to 1 v of s square 1 half. So this is called the Gersanov theorem. I'm just telling you that, so the idea is as follows. You are making a change of variables, and but then you want the invariance of the distribution, and that can be done by change of measure. So it's almost like I told you about this, right, already. If you have just one normal random variable with a mean, then you can shift by the mean, right? And I showed you that it is nothing but looking at the density function, right? You keep one part of it and the rest of it would be exactly what you have here. This is, of course, much more sophisticated. It's almost like saying, supposing you fix a point on the real line and it is the number 4, then it's all with reference to the origin. If you just make a shift, you can make it look like 2 if you shift the origin. Maybe that's not a good thing. Okay, so why did I say this? One way is, for now, assume this to be so. Namely, you change the measure, and something that was previously a Brownian motion, you took out something and still it would look like a Brownian motion because you changed the measure. This is something abstract. You have to learn the Gersanov theorem correctly. And that's an assignment by itself, meaning it will take several days. So now let me, for just the pleasure of it, compute the following. Logarithm of derivative of nu v with respect to mu, which I have written there, d nu v. What is that? That's exactly just the, we already have it there. V of s dws from 0 to 1 minus 1/2 integral 0 to 1 v of s squared ds. And what else should I do? I had to take the expectation of all these under gamma nu, right? Gamma v, or nu v, whatever it is. That's what it is. Any idea how to make it how to make this term disappear? Yeah. So there is a w here, but under gamma nu it will be nice to have a w tilde, right? Therefore, instead of the dw, you also have minus v of s ds, right? So you can write this as integral 0 to 1 v of s dw tilde. Yes. But what have I done now? There is a dw, but there is also a v of s ds also, which will multiply this v of s ds. And then I'm going to subtract, right? Okay, this part is a little bit hard. Actually, I don't expect anyone to jump with joy here. Unless you have seen this before, it's hard to believe this. Nu v. Now, this is a Brownian integral, therefore expectation is 0. All right? And then these two things will give you just, they will cancel at least halfway, and you will get it to be 0, 1. d of s ds. Okay. So let me also add a little bit to this. Okay, so this is one statement. I can give it a name here. This is called the relative entropy. It is written as usually mu v mu. And it's a lower semi-continuous function with respect to the first argument and has some nice properties. Okay. So if you have R of nu v mu plus, I take some function and then I find a d nu v. For some reason I do this, let's say. I already know the first part. It is 1 over 2 g nu v integral 0 to 1. And f is actually defined on the path space, right? F has a domain in the path space. Okay. Yes. Now, if you give me 1 second. Oh, I didn't put the second part here. That's why. And then here, what I can do is expectation nu v. It is f of w, meaning omega, right? But instead of w, I can put w tilde plus integral, right? 0 to 1 of b of s ds. And that is subtracting and adding the same thing. That's all there is to it. So now you inf over all the d, and there is a theorem that says that w tilde, well, just 1 second. So given any bounded Borel measurable function, on omega, if you are trying to capture, let's say, if you try to calculate minus logarithm of expectation of e to the minus f of w, that would come out to be the infimum over v of all these things on the right hand side. Infimum of all these. Huh? I'll just write right hand side of 2 instead of writing all these things again and again. This is 2. Okay, this equation, let's call it as 2. And this is a theorem. What is it called? It is called the relative entropy theorem. So you can always give it a. There is no limit. Yeah. Okay. And this same thing can also be done with the expectation not under this new measure, but under mu, namely the original Gaussian measure, or the same thing almost. 1/2 is there, of course. Absolute V of s squared d s plus f of w plus integral d of s ds. How this became from expectation with respect to this measure to the expectation under mu, that's a long story. Now, what this theorem that I have written is called the representation theorem. Actually, it's a very long proof, right? So this is called the representation of positive functions, right? So what does it represent? It represents positive function, expectation of positive functionals. It's precisely these kind of functionals that we need here, right? because your x super epsilons, if they are solutions of, let's say, stochastic differential equations, strong solutions, they'll come out to be functionals of the Brownian motion. Not beautiful functions, but Borel measurable functions. All right, so pretty good. And then this Borel's Laplace principle has to be proven for nice functions. Where is it? Oh, CB. But your x super epsilon is going to be a measurable, Borel measurable function of the Wiener process. So when you compose a CB function with a Borel measurable function, it's still Borel measurable. Right? And then, therefore, this left-hand side here in the Laplace principle can be actually computed in this way, can be given a variational formula in this way, right? And we got to make use of this in order to prove the Ventresel-Friedlin rate function. So that's the idea. So let me do you want me to go another 20 minutes? I can. Okay. You are not tired, right? Okay. This was the rough part, so to say, because I wanted to hurry on up and then do this representation theorem. This representation theorem was due to Bouvet and Dupuy and others. We made use of it for proving, Sri and I wrote a paper on large deviation principle for stochastic Navier-Stokes equations. And then shell models with Utpal, and then now Utpal is doing things on processes with jumps and with Manil, and several others are excited about this way, wherein you don't have to compute, you don't have to discretize processes and compute probabilities and so on. Rather, simply use this representation theorem and connect it to Vardhan's large deviation principle, and then identify the rate function. All right? Okay, so in the rest of the 20 minutes, it should be pleasant because I have now introduced all the ingredients. And the main thing was to come to this. This itself, when I saw it first, I liked it quite a bit. We were all very excited. Some of my colleagues at LSU told me that, oh, if only they could have proved such a thing for something as basic as the Wiener process, they could just relax for the rest of their lives. You know, it's so beautiful. And I think so too. And because it is for bounded Borel measurable functions. Yeah.
What is the process?
Yeah, this is the Wiener process.
Can I ask something?
Yeah.
Because I see the formula and I see one of the pieces due to the camera magnitude.
Correct. That's right.
When you pass to the Levy process, you lose this kind of change of variable because you don't have the structure of camera magnitude space. So I don't understand very well how it can be possible to formulate in a simple way large deviations principle with Levy processes.
Good question. You should talk to, there are so many jump experts here who have been jumping quite a bit, so you should talk to them. Yeah, I think it can be accommodated. Yeah. Professor Manna, Professor Rudiger, and so on, they should be able to solve your problem with your basic question, right? Okay, now we will come back to where we were. It's very smooth sailing now. So consider dx of t. I'll introduce a whole bunch of like-minded equations. X of t dt plus sigma of t dw of t xv of t. I'm setting up the notation here. V of t x of t dt plus sigma of t dt w of t plus c of t dt. So there I could have combined these two, right? They are both dt terms. And so on and so forth. So what is this represent? Let's say that there exists a strong solution. Suppose there exists a strong solution. Both have a dw, so nothing is still deterministic or anything. And how can we write down minus log expectation e to the minus f of x?
So is it x v in p or just x?
Say that again.
X in the p term, is it x or xp?
Good question. xv. Good. So everything xv. So no complication there. Nothing coupled and all that. So if you want to do this expectation, any ideas how to do this? Where f is, let's say, a nice smooth function, continuous bounded function, right? Then capital X, because it's a strong pathwise unique solution and so on, it is going to be a functional of the Wiener process. So put them together, you get, right, Borel measurable function of W, right? And the Borel measurable function of W can be writable in this way, correct? Okay. So I'm just going to write down whatever. Integral 0 to t, not 0 to t, 0 to 1, because that's my time interval, let's say, ds plus f of x. For all f bounded Borel measurable. Is that obvious? Yeah, it is. So here is f of x, right? And I need this v of s squared and so on, because I can convert everything to anyway a functional of the Wiener process. So this has nothing to do with what function we put in here. And in here it would be a function of, so the same function, right? But instead of x, you got to put w plus x is a function of the Wiener process. Instead of the Wiener process, you should put w plus integral of v. So in this, if you put w plus integral of v, then dw will give you dw. When you take the differential, it will be a dw plus the v will be there, sigma times v dt. That's why it is here. So I wrote it all as xv. Okay. So this equality is straight from 3, if we call this as 3. From 3. All right. So that's done. Now we will go to, so there is no epsilon anywhere. Now we will introduce small noise asymptotics. Oh, I haven't used this board. What should I erase it with? Anything?
Any one of those.
Oh, this small one. Okay, I'm almost done. So, so now I would like to introduce X epsilon process. What is X epsilon process? It will have a square root of epsilon in that first equation, all right? You can use square root of epsilon times sigma instead of sigma. In equation 4, there is no 4. Let's call this as 4. Let's also call this as 5. And X epsilon V, use square root of epsilon instead of sigma in dW term. In 5. But don't disturb this. It is just sigma V. Only here there is a square root of epsilon. Okay. Then what happens is now the theorem of, so that's the notation. All these x, xv, x epsilon v. So here only. So don't put the square root of epsilon in the last term in equation 5. So now the Ventesel-Friedlin theorem. What did they say? We might have forgotten, right? Ix of f it was going to be integral 0 to 1 norm, not norm, just this ds. And the infimum is over V, number of L2 of 0, 1 or D, such that f of t is x plus or f dot of t, let's say. Is b of t, f of t dt plus sigma of t, f of t, f t, t. You all remember this, right? Well, I don't. And, it's very difficult to remember these. Okay, is the rate function. For the X epsilon process. Now what you do is, I'll just prove, give you an indication of the proof rather for 5 minutes. I'll just tell you the broad ideas. There isn't much in the upper bound. So what I'm going to show is, we will show that lim sup as epsilon goes to 0. So I'm going to use the Laplace principle. Minus epsilon, oh well, minus is there, okay. I could even put the minus sign on the other side, it doesn't matter. Logarithm of expectation sub x of e to the minus g of x sub epsilon divided by epsilon. Let's see if that is really what we want here, right? So instead of h, I wrote g, that's all right. Division by epsilon, there is a minus sign, logarithm minus, this minus sign, I just brought it to the other side. It's not a big deal. I'm only doing the lim sup to be less than or equal to that right hand side, where I is given by this, right? There is no negative sign because I took it already. What else should I have there? Infimum of g of x plus I of x over x. Okay, that's very easy. Correct? So instead of proving the Laplace large deviation principle, we are using, we are going to show this Laplace principle. This is only one side of the bound. All right, and then I had to take the lim inf and show that it is also greater than or equal to, because I want an exact equality here, right? But I won't have some parts are very long. Last time? Too difficult? Yeah.
So this, what you are trying to show is for starting with lim inf here or lim sup there. I think it's because the negative sign you are taking inside, right? So
That's right. That's right. Yeah. So I just call this as the upper bound. You are right. If I didn't take the minus sign, it would have been the lower bound, right? Yeah. Very good. And what shall we do? So make use of the definition of infimum here in order to pull an optimal. It is I plus g, right? We are taking the infimum. Therefore, there has to be an x sub 0. I'm just going to call it as pi sub 0, which is going to be less than or equal to the infimum plus delta over 2. So use the definition of infimum. And so let me go to another side of the board. This is good. I don't need that. I don't need that part. Okay. And once I fill this board, I'll finish it. Okay. But it may take me some time to finish this board because I don't write as big as 3. So what shall we do? Let me quickly do this. Take any delta. And here, of course, G is bounded continuous, right? G is a continuous bounded function because that's all that we need. Take any delta. Choose a pi sub 0 such that, I could have called it as x sub 0. I see whether, now you will notice that step by step, it's all going to be obvious because we have already done the hard work. Okay, now what is alpha? I'm going to call this value as alpha, all right? Alpha, say. So by definition of infimum, you should be able to find a pi sub 0 for which the actual value of this is going to be less than or equal to infimum plus delta over 2. Oh, I don't need, I can even put just I. I just wanted to say that it starts at x. Yeah. Let's see, why, step by step, I thought it should all come out very easily. d0 of s squared ds is less than or equal to ix of pi 0 plus delta over 2. Now I'm going to ask you all to help me, because I don't know the reasons. So you can tell me, why is this second statement true? Pi 0 has already been ascertained, right? That's from the definition of infimum. Okay, using that pi sub 0, how can I claim that there exists a v sub 0 satisfying this? Well, it involves the I. So if you put the I of pi sub 0, that's an infimum. So again, I can use the definition of infimum, right? And it will give me a v sub 0. So both are actually just definitions of infimum. Okay. Pi 0 of t. I'll just keep writing some things. And pi 0 of s ds. Sigma of s, pi 0 of s. V0 of S. Why is this true? Huh? Because that's the connection between V and pi. Now, lim sup of minus epsilon logarithm Ex x super x sub epsilon divided by epsilon equals I'm going to write something else here, infimum over V dx 1/2 integral 0 to 1 d of s squared ds plus g of x epsilon v. Why is this true? Oh, right. Instead of f, I have some g epsilon divided by epsilon, g of x epsilon divided by epsilon. So that's straight from the representation theorem. Correct? And what is x epsilon v there? There, I have it here. That's the correct dynamics. And this is going to be less than or equal to lim sup as epsilon goes to 0. So these are all lim sup as epsilon goes to 0. I just added those, though I need not have introduced it so early. Ex. Ex means we start at x. Integral 0 to 1 0 of s squared ds plus g of x epsilon v0 Why is that true? Is that true? So what have I done there? I have just put the v sub 0, and v sub 0, what is v sub 0? Exactly, it's in that set, right? So instead of the infimum, I have taken 1. Okay, very good. So I want you all to observe that everything is a very small step here. And this is going to be equal to 1/2 integral 0 to 1 v0 of s squared ds plus lim sup as epsilon goes to 0 of v sub x g of x epsilon v0. Why is this so? Maybe I should add a delta over 2 or something? No need. No, I just pulled this out, and this is the only place that epsilon depends on, so this is obvious. Maybe it's an equal to, but I don't care. Yeah, okay, equal to, all right. And this is going to be less than or equal to I of pi 0 plus delta over 2. Maybe I need an expectation there also, but everything will now become deterministic, plus this term. That's all right, because that's how we chose it. Okay? And now we come here. X epsilon v0, where does it converge in distribution to? It goes to, my claim is it goes to pi 0. Okay? Therefore, continuing, this quantity will become less than or equal to I of pi 0 plus delta over 2 plus g of pi 0. Right? Okay. Because g is a smooth function, remember? And this is less than or equal to infimum I ix or I, where you can put x there also, just to remind ourselves that the starting point was that plus delta for all pi member of in the space omega or whatever. Why is that so? Choice of V0, correct. So the delta over 2 has become delta is arbitrary, we are done. So that at least gives us some indication as to why how this rate function comes via Laplace principle. That's all I wanted to show. And I wanted you to observe that we did a couple of different things, namely Laplace principle as well as this representation theorem. How to put them together, and then when you write down, it's all almost elementary, right? It's even difficult to remember because it's step by step, so easy. And likewise, you can prove an upper bound as well. Sorry, this is what I called as upper bound. You can also prove the reverse inequality with limits. And once you do it, the theorem is over. So this was the famous Ventresel-Friedlin theory. And this is the one that helps you to find all these kind of paths and so on and so forth, right? So there are all kinds of problems wherein a large deviation principle is useful. In fact, people are studying on this side. Oh, maybe I will erase this. This is, I'm sorry, time is up, but then I'll just make one statement. So let's say that there is a population, and then here is the population of people who have recovered from a disease, all right? And in the y coordinate, you are measuring, let's say, the percentage of population who are infected and recovered, okay? And you are trying to see the probability of extinction of this disease, which is a rare event. So then you find this, you use this ansatz and then try to minimize the I of x over this rare event. And then wherever it minimizes, that path is going to be called as the most probable path in that rare event. So if you want that rare event to occur, it is going to most probably occur this way, all right? So let's say it goes like this, maybe. All right. So what am I measuring here? I'm measuring the number of people who are recovered, right? And this is infected. If this is the most probable path for extinction of the disease, okay? So extinction means everybody is good there. Then what you can do is you measure what has happened in real life. You can estimate, right? And then you are here, let's say. That is, the number of people who are recovered are given by the x-axis coordinate, and the number of people who are still infected are here, right? So then you want to push this point over here. So you want more people to be infected. How would you do that? Cut out the vaccination. Then more people suffer, and then you are on this. You are on this. Supposing you are somewhere here. Then too many people are infected. So do a lot of vaccination and bring it down here. So try to adhere to this most probable path. And that's one way to make it useful. Yeah. So we can do all this by, it may look like all this writing is just some mathematics and who cares, right? But really you have the population dynamics here, and you can actually go and infiltrate into the system and then adjust the system, right?